So today we're going to discuss the synthesis of the acetyl salicylic acid lab. Now, acetyl salicylic acid is kind of a tongue-tire name for the common name of aspirin. And you see the structure shown there in the box. So now aspirin is a pretty fascinating compound, and there's a lot of active research still being done in some of the medical benefits of aspirin. And if you take a look in the book that you have, there's a nice essay is what they call it in the book, a nice essay about what aspirin is being used for and kind of what the research is with it. But for today, what we're going to be looking at is an esterification reaction. So to form acetyl salicylic acid, we're going to change a hydroxyl group on a benzene ring to an ester functional group. And we're going to do that by using an acid. So we're going to use some protons here. So a Bronsted acid is going to help us transform a hydroxyl group into an ester group. So we're doing an esterification, and we'll talk about the mechanism in just a minute. In terms of techniques of what we're going to be doing, we're going to be talking about recrystallization. That's for purification of our product. We're going to use vacuum filtration to separate solids from liquids. And we're going to use melting point to determine purity, or one of the methods that we're going to use to determine purity. And so we'll talk about all those techniques in the following slides. So let's look at the reaction and the mechanism for the synthesis that we'll be doing in today's lab. So we're going to be taking salicylic acid, which looks like this. So I've got a carboxylic acid group and a hydroxyl group. We're going to be reacting that with acetic anhydride, which looks like this, and we're going to be adding some sulfuric acid as a catalyst. Now, in reality, we can use many different kinds of acids to do this reaction, but sulfuric is what we'll be doing in this particular lab. And when we mix those together, what we're going to do, the carboxylic acid portion stays the same, but we will be turning our hydroxyl group into an ester, and that ester portion is coming from the acetic anhydride portion over here, boxed in the green there. So let's go through and take a look at how the mechanism for this is going to work. Now, before we start, I just want to make a quick note. For the mechanism, I'm going to have HA like that. That is going to be our sulfuric acid. So I'm just going to have HA represent sulfuric acid. And if you see an A with a lone pair and a minus, right, that is our conjugate base, right, the hydrogen sulfate ion. So just so we are all on the same page there with how this works. Now, we are using an acid, and if you are going through an organic mechanism and you see an acid, usually that's going to be used in the first step. It's going to be used to protonate something to kind of help the reaction proceed along. So the first step is going to be a protonation of the acetic anhydride. So there's my HA. Okay. So the acid protonates the acetic anhydride. So we end up forming this. And don't forget the plus charge there now. The salicylic acid comes in, lone pair hits the carbonyl carbon, and pops up the double bond. So we end up generating this species. That plus charge there. Okay. Now something needs to come in and clean up here a little bit to the conjugate base, the A minus. Comes here, grabs that hydrogen. Right. And so we end up with this after that first set of arrows there. Just clean up a couple stray marks there. Okay, so now for the next step, we need to bring our acid back in. So I'm just going to change colors here just so we can follow for just a second. So I'm taking those red lone pairs there, right? So the red lone pairs on that central oxygen there. Those are going to come in, grab that hydrogen, and let's follow to down here. Let's make that bond there in red to that hydrogen there, plus charge there. Okay. Now we have a unique set of arrows that come in. Let me pull in some red arrow, or excuse me, the red color here. That's going to come down to make a double bond, and we're going to kick off that portion over there, right? A protonated oxygen makes a very good leaving group, so it's going to end up leaving, right? So there's that part over here. And on the other portion, what we have, let me see if I can draw this to kind of maintain the way things are aligned. Right, there's my benzene ring, there's my carboxylic acid, which we haven't done anything with. There's that oxygen, right? It's now doubly bound to that oxygen, which is protonated. And just so we can see what we're doing, I'm going to make that oxygen in purple here, right? And that oxygen in purple over there. So hopefully that kind of helps clarify where things are. So now the last step, all we need to do is kind of clean up and get rid of that one protonated hydrogen there on the oxygen. So again, my conjugate base is going to come in and clean up. And at the end of the day, right, there's my ester and the carboxylic acid there. So fairly lengthy with the mechanism, but all we're doing is protonating the anhydride, the hydroxyl attacks, there's a transfer of protons around, and we end up making an ester out of that initial hydroxide. So let's talk about recrystallization. Now in today's lab, what you're going to be doing is you're going to purify your compound by recrystallization. Now recrystallization, if we take a look at the bottom there in the white, it's kind of visualization of what we're going to be talking about. You're going to start with a mixture of compounds over there in number 1. You're going to add a solvent to it. You're going to add a solvent to it. You're going to heat it up, right? You're going to heat something up. You're usually going to end up, you might have to end up filtering. And then you cool something down. And hopefully you'll see some crystals start to form. And an example of crystals is over there with the red highlight. Now crystals do come in all shapes and sizes, and there's a lot of science that goes into the formation of crystals. So your crystals may or may not look exactly like what you have there, but just understand that you should see some kind of regularly shaped solid come out of solution, and that's how you kind of the first indication that you have a nice set of crystals. So you're going to start at number 1 there in the green. You're going to add some solvent, heat it up. You might have to filter it just depending on what you're working with, and then you cool it down, and once you cool it down you should see some crystals form. So let's talk a little bit about recrystallization, kind of some of the details that go into it. So in general, recrystallization is a purification technique. So we are using this to purify whatever it is that we're dealing with there, right? Now, if you recall what we talked about crystals, at least from the first or second semester of general chemistry, right? They're regularly arranged molecules. And so to form a crystal, you have to have the same molecule aligned in the same way. So think of it as if you're building a house made out of bricks, right? Bricks are a very regular shape, and you have to line them up in a very specific way, right? You have to fit them together in a very specific way to make the wall of your house. And so crystals work the same way, where instead of bricks, you have the molecules themselves. So the bricks align themselves in a very specific way. Now, if you imagine that you're trying to build a wall to your house, and you're using bricks, and then all of a sudden you have a cinder block, right? It's going to throw off the integrity of that wall. It's going to throw off the shape. And that's the idea behind recrystallization. You're keeping only the bricks and you're getting rid of the cinder blocks. So you're keeping one molecule but excluding the other from the formation of those crystals. And so it really comes down to the solubility of not just the crystals, but also the molecules and the compounds that are in solution. So your solubility and your solvent is going to be playing a huge role in how we can recrystallize these compounds. And if you think about one of the other lectures and one of the other labs that we have, we talked about solubility of liquids and solids with respect to organic chemistry. So the principles that you learned in that lab are going to come in when we're dealing with recrystallizations also. Let's go through a visualization of the purification by recrystallization. So it's going to be a pretty heavy slide, so let's pay attention to, I tried to break it up for you, but let's pay attention to what's happening. So let's say that up in the top left-hand side, we have a mixture of compound A and compound B. And we add some solvent to it, right? And we heat it up and then we start to cool it down, right? So we have let's say that the solubility is 10 milligrams of A and 10 milligrams of B at room temperature, right, at around 20 degrees Celsius. As soon as we heat it up, though, right, we increase the solubility of A and B so that pretty much everything goes into solution, right? So the difference is we want something that's soluble at high temperature, right? We want a solvent that makes everything soluble at high temperature, okay? So we cool it down, right, and we get to the next set of steps here. After we cool it down, right, we go back to our solubility, which was the same as for this step here, right? So the solubility here is the same as the solubility here. So now we can filter and remove, right, some of our insoluble compounds. Okay. So we add some more solvent, right? We cool it back down, right? We recrystallize and we can separate out, and at the end, right, we lose some of A and we remove the last of B, our impurity there. So if we take if you want to take a pause here and kind of look at what's going on with this slide, once you kind of read through it, it'll make sense to you. But the basic steps are to dissolve something, right? Get a solvent, dissolve your impure compound in there, heat it up, right? Heat it up, let it cool down to get your crystals to form. We filter out that initial batch of crystals, right? And then if you look at the way this is drawn, right, that in green right there, we take that and put that back into our vessel to recrystallize. So we heat it back up again and cool it back down again. So it's a recrystallization. We heat and we cool and we heat and we cool. So hopefully this visualization kind of helps you to make sense of what's going on with that. So as was mentioned in the previous slides, it's really going to be important to choose the correct solvent. Now for the lab that you're doing today, you will be using something called ethyl acetate. Which has this structure to it. So it's an ester. It's more commonly used these days as nail polish remover, so the more frequent the more common nail polish removers now are using ethyl acetate, so it's something that you can actually buy in the store, so to speak. But for the solvent for today is going to be that ethyl acetate. And so just to summarize what we talked about, the proper choice of solvent for recrystallization, you must dissolve your product while it's hot, but it should have a low solubility of our product when it's cold. But our impurities should remain dissolved, right? That's kind of the key. And so that's a pretty hefty demand of this solvent, right? It's got to dissolve something hot. It shouldn't dissolve it at cold, but it should have some of it dissolved in terms of the impurities. So how do we go through and do this? So let's say that we have a lab where I need you to figure out how to recrystallize something. So we got to do a little bit of tests first. So in general, we can take about 0.1 grams of the solid to test and dissolve it in about 2 to 3 milliliters of solvent. If most of it dissolves at room temperature, right, then it's not a good solvent. Remember, we shouldn't have lots of solubility when it's cold or at 20 degrees Celsius, right? Not a good option at that point. If little to none of it dissolves, at room temperature with heating, it's not a good solvent either, right? If we heat this stuff up and it's not dissolving anything, well, we can't do anything with this in terms of recrystallization. If we get the last result, right? If we get the last result where it dissolves when it's hot but not at room temperature, we still are not 100% sure whether it's a good choice. We have to do a little bit of testing with that too, okay? So this last box here at the bottom is kind of the steps of how to check if you have a good solvent for recrystallization, right? You need to take some of your product, try and dissolve it in your solvent, and try and heat it up to see if it does or it doesn't dissolve in that solvent. Let's briefly discuss the technique of vacuum filtration. Vacuum filtration is going to be a common technique that you guys use throughout the semester, and it's mainly used to separate solids from liquids. So say for instance you had a glass of water and there was some sand in there. If you wanted to be able to separate the sand from the water, the solid from the liquid, you could set up a vacuum filtration to do that. Now you need a couple bits of equipment to do that. First thing you'll need is a sidearm flask, also known as a filtration flask. It basically looks like an Erlenmeyer with a little hose barb coming off the side of it. You'll need a Buchner funnel. These are either plastic or ceramic and they've got holes at the bottom of them. You'll need some filter paper because you're going to have to cover up the bottom of that Buchner funnel. And then you're going to need a vacuum source. We have house vacuum that are plumbed into every one of the fume hoods. That is where you conduct your experiments, so that'll be the vacuum source for you guys. You basically put all that together, assemble it like that picture shows there. You got your vacuum source with the red tubing coming off of there. You have your Buchner funnel with your filter paper inside of it. And that's how you'll get that set up. The only thing I will say about this is make sure you do clamp down your setup when you have it all finished. These do have a tendency to kind of fall over since they are top heavy there with the Buchner funnels, and if they do fall over, not only might your equipment break, but then you'll also lose your product that you have in there, and that means you're going to have to start your reaction over again. So do yourself a favor, always make sure that you are clamping down your Buchner funnels when you go through and use them. We will be using melting point as one of the techniques that we'll use to test purity for compounds. And there's a picture of the melting point instruments that you guys see there on the right-hand side. There's a couple of points that I want to make about melting point itself. The smaller the melting point range, the smaller your melting point range, that usually has an indication of higher purity. And it is important to note that when you quote a melting point, it is a range. So it's something like 100.1 degrees Celsius to 100, let's say 100.5 degrees Celsius. There aren't many melting points that happen at just a single temperature. So when you're going through and recording your melting points, always make sure you put a range in there. Now these are a comparative purity technique, which means you're going to have to compare your crude product versus your purified product. So for instance, for the acetyl salicylic acid lab, you're going to be comparing your crude product versus your recrystallized product. So remember, we're going to recrystallize this stuff from ethyl acetate. So when you get your melting point, you're going to need to do the melting point twice, once for your crude and once for your purified. And don't worry, you can do that both at the same time. These melting point instruments let you run, I think, up to 3 samples at a time. So all you have to do is prepare your samples properly, and then you can do that at the same time there. Now your TAs are going to give you guys specific instructions while you're in the lab about how to set it up. I'm not going to list that out here, but they will walk you through kind of the buttons to press, but it's pretty simple to set up. But how do we actually prepare our samples, or what do we need to run a melting point? Where you're going to need the actual instrument itself, and that's fine. You probably figured that out, right? You're going to need to know, you're going to need a capillary tube, and your capillary tube is basically this guy over here in the photo there. Your capillary tubes are just these glass tubes that have an open end on them, and you're going to have to pack your sample. Okay, you're going to have to pack your sample into that. So you're going to get the open end and tap it gently into your powder. And after you have a small little bit of your sample in that tube, you really do not need a lot. You do not want a lot of your sample in there. Very, very, very small amount, like it says down here at the bottom. Let me just highlight that real quick. Really, you only want 1 to 2 millimeters of your solid. You do not need a lot to get this to work. So you gently tap the open end of your capillary tube into your solid, and then you're going to need to pack your sample, which there's a glass tube that we use, the packing tube. You're basically going to drop your capillary tube through this packing tube, and it's going to force it down to the bottom. And again, don't worry, your TAs are going to show you how to get this set up. But the key part I want to make about the equipment here is that you only need a very small amount of your of your solid in there to check your melting point. If you put too much, it's gonna throw off your readings. You're gonna get a larger range with your melting point there, and that's gonna throw off some of your data. So to conclude this presentation, you're going to be conducting the synthesis of aspirin, also known as acetyl salicylic acid. You're going to follow the procedures that are in your lab manual. There shouldn't be any changes from what is written in there. You're going to purify that by recrystallization. After you've done the recrystallization, you're going to check your melting point, and don't forget you're going to compare your crude versus your recrystallized. We are going to add in NMR and IR, and your TAs are going to walk you through that. That is not something that is in the manual. These are some new instruments that we got, and so we're going to be using these for pretty much every lab that you guys will be conducting this semester. So in addition to the melting point and the procedures, you're going to be running through NMRs and IRs, and your TAs will be helping you with that. When you're doing after your recrystallization, when you're ready, don't forget to set up your vacuum filtration, and don't forget to clamp down your setup. You don't want to have this knocked over in the last step there and then have to start all over again. Don't forget proper notebook usage. You're going to have to take some good notes and observations when things change colors, or how does your product look, or was there anything unusual that happened, or any steps that might have had to have changed a little bit. Take good notes while you're going through. Don't forget to work quickly and efficiently, right? And the best way to do that is to make sure that you're prepared ahead of time. Please read through your lab book. Please write good notes in your lab manual. Make sure that you're prepared before you come to lab, and then you will be working quickly and efficiently.